Hello, friends. Once again, welcome to my class on plasma physics. Friends, in the previous class, I discussed the motion of particle in uniform magnetic field, and I described the trajectory of the charged particle, and I described the motion of electron and ion in a uniform magnetic field, and I described the diamagnetic behavior of the plasma, and we found equation of motion of the charged particle. Today, we will discuss the motion of particle in uniform electric as well as magnetic field. So we have a combined field, and we want to understand the motion of a charged particle in the combined field. So let us consider a Cartesian coordinate system and consider a particle of mass m and charge q is moving in a uniform magnetic field B and uniform electric field E. Look at the figure here. I applied the magnetic field along the z direction. The field is uniform. That means it is constant and having the same direction along the z direction. And the electric field is applied along the xz plane. It's a uniform electric field. It is applied in the xz plane, which you can see from the figure that you have an electric field which is having the x component and having the z component. And so you see here in this case, a particle experience a Lorentz force. You can see that this equation I wrote here, that particle experience a force, and this is because of mass into acceleration. So I write a rate of change of velocity, that is m into a, uh, and the right hand side of this equation, because we have the combined field, we have electric field and magnetic field together, so particle experience a Lorentz force. So here you see that I wrote the expression of the Lorentz force where Q is the charge carried by the particle. You have ion and you have electron. So we have to take care about the sign when we write the expressions of the Larmor frequency and some other expressions that we will take care. This is the electric field which is applied along xz in the xz plane, and we have these the product vector product b cross b, which where v is the velocity of the particle. And here you see once again, let me explain that let us take the z-axis of the coordinate system along which you apply a uniform magnetic field. So I can write your magnetic field B is having only z component, because there is no x component, there is no y component. So we can write in a Cartesian coordinate system bzk, and then bz is b. So the magnetic field we can write in a vectorial form, magnitude of b in the direction of k. Here b is constant, please remember. And here you see, I once again let me say that we take xz plane so that it contains your applied uniform electric field. And so electric field are having two components. Now we have a ex and ez component because it is applied in xz plane. So ex and ez are the constant component of the electric field along the x and z axis respectively. So here, friends, you please remember we want to study the combined field. You know, in the previous case, we found that the trajectory of the particle is a helical path, and you see that there are two components of the particle velocity, the parallel component and the perpendicular component of particle velocity. And when there is only uniform magnetic field, we found that the parallel component of the particle velocity is not at all affected, and it is moving with a constant velocity, and the perpendicular component of the particle velocity is affected, and because of that there is a circular motion of a particle in xy plane. and there is a motion along the z direction because particle is having some initial velocity component along z direction, so you will have the helical path. Now since we have an electric field along with the magnetic field, because of the application of the electric field here, we will see that particle will be accelerated because of the z component of the electric field, and we will have a effect of electric field. Because of that, a particle acquires a additional component of velocity in addition to the parallel component as well as the perpendicular component, and this additional component of the velocity which is acquired by the particle is referred as the drift velocity. And we want to understand what is the drift velocity. We want to see the physical significance of the electric drift, because the drift is caused because of the application of the electric field which we have applied along with the magnetic field. So we want to understand the physical interpretation of the electric drift, and because of the application of the electric field, particle acquires a component of velocity, and that component of velocity is known as drift velocity. So now I would like to explain the concept of a drift velocity, as well as we will see the equation of motion of charged particle in the combined field. So now let us see that since particle velocity we can write in a Cartesian coordinate system is Vxi plus Vyj plus Vzk. This is the Cartesian coordinate representation. And since we want V cross B in a Lorentz force, so I calculated here this equation number one is the force acting on the particle that we have discussed. And now we write this equation number two. Look at your equation number two, which I calculated V cross B. So I take a vector product of velocity vector with the applied magnetic field, which is a uniform magnetic field, which has only z component. And since we have Vz is equal to B, I wrote the determinant of V cross B is Ijk, Vx, Vy, Vz 0, 0, because Vx is 0, Vy is 0, and Vz is B. So I can write V cross B is simply Vyb in the direction of unit vector I minus Vxb in the direction of unit vector J. So this is the vector product which we calculate. This is the vector. So we write V cross B. So V cross B we will substitute here in equation number one to find out the component of the force experienced by the charged particle in the combined field. So let us work out to study the equation of motion, and we will find out the component of the forces, force, which we'll see. So you see these are the two equations. Equation number one, which I am writing here, and equation number two. So once again, I'm rewriting both these equations for your reference here. So this is your equation number one. This is your equation number two. And now you see I write down this vector V in a Cartesian coordinate system in equation number one. So you see I write m d by dt and velocity vector V. I write down Vxi, Vyj, Vzk, and you see this is the charge carried by the particle. So I write Q. Here I write the vectorial form of vector E because it is applied in xz plane. So I write here Exi plus Ezk in place of vector E, and V cross B, which we have already calculated in pair. This is the V cross B value, V by Vi minus V, this minus Vxbj, which we will substitute here. So you can see this is I substitute here V cross B, right? And now you can see this expression. So I simplify this expression because this is a time derivative of Vx component. So it is mVx dot I, time derivative of y component. So it is mVy dot j, time derivative of z component. So it is mVz dot k. This is simply Vx dot is time derivative of x component, right? And that is known to you. And this is the right hand side. You can see right hand side I simplify the expression, and I combine the ith term, that is the I combine the ith term and I combine the jth term factor. You see, this is the expression which you can understand and you can write down in this manner. Okay, so you see this value you can find. I can this is very simple. You can simplify. You open the bracket, combine the item, combine the jth term, and combine the kth term, and now you compare the coefficient of ijk. When you compare the coefficient of ijk, you can write this is the coefficient of I, that is mvx dot, and this is the coefficient of I here. So of course it is multiplied by q, so you can write qex qby. You see this y component of j, so this is the jth component is here. So there is a vector j here, vector j is mentioned here. So you can write mby dot is, there is a minus sign, so minus qb vx, and the component of k. You see the k vector. If you compare the vector k component of vector k, so you can write mvz dot is equal to this q is a product, so q is z. So these three equation we have obtained. So please remember, so we have equation number 3, we have equation number 4, we have equation number 5. Please look at this equation number 1 once again. This this equation of motion, which indicates the contribution of Lorentz force. Equation number 2 is indicating the vector product of V cross B. And equation number 3, equation number 4, equation number 5 is simply giving you the component vector and time derivative of Vx dot, time derivative of velocity component of x direction, velocity component y direction, and velocity component z. This you remember. Right, now you can see this equation number 3, equation number 4, equation number 5. I first take the equation number 5. So I'm writing this equation number 5 once again. Mvz dot vz dot is d by dt of vz, right, is equal to qez. Now I integrate this equation with respect to t both the sides. So when I integrate it, this is vz dot, right? So I will get Vz. If you integrate this equation with respect to t, so we'll get Vz. And if you integrate this equation with respect to t, that is Qez t divided by m, and we have to write a constant of integration, that is Vz0. This is very simple step and you can work out. And this is I have already explained in my previous class also. So I am taking this step directly. Okay, and now you see that Vz0, which I wrote here, is basically a z component of the particle velocity at time t is equal to 0. Please remember, you see in the previous class I said that if Vz0 is 0, then particle will only describe a circular motion in xy plane. But if Vz0 is not equal to 0, then particle will describe not only a circular motion, but it will move with a constant velocity along z direction. So you have a linear motion along with the circular motion, and resultant path is the helical path, which we have discussed in the previous lecture. So here again, once again, I am considering that Vz0 is a z component of the velocity at t equal to 0. So here you see the velocity of the particle along z direction, this Vz, is a function of t. So velocity of the particle along z direction increases linearly with respect to time. Because of the application of electric field, you see that Ez is what is Ez? That is a Z component of the applied electric field, which is constant, of course. But because of this constant component of electric field, your particle velocity Vz, that is, you see that Vz is increases linearly with respect to time t. And now this is basically a rate of change of displacement. D by dt of z is vz. So if I integrate this expression of velocity, so you see I integrate with respect to t. So here I have mentioned this step very clearly. You see this vz. So vz is simply dz by dt. You can see this is the rate of change of displacement along z direction, is giving you vz, velocity of particle in the z direction, z component of the particle velocity, I would say. So this is known to you. And now you see I integrate this. So this is q e z t m into dt plus the integration of this term vz0 tt plus we have to write some constant of integration z0. Please remember this. So I can see simply this is the left hand side will simply give you the z displacement of particle along z direction, is giving you q e z divided by, because this is t square by 2, integration of t square by 2, so it is t square upon 2m. So this is the factor q e z divided by 2m, which is constant here, you see. And then this is giving you t term, so v z0 t plus z0. And this is a equation which is similar to your Newton's equation of motion. Distance d is equal to v0 t plus 1 upon a half at square, right? This is the equation for an accelerated motion which you have studied at your school level, right? When you study the Newton's law of motion. So this equation represent that, showing that the distance z changes as t square. Z is a function of t square. So the particle is accelerated along the z-axis due to the z component of the electric field, where z0 is constant. Z0 is basically a component of the position component. I would say that is the component of the particle at t equal to 0. Z component of the particle, I would say, at t equal to 0. And you see it is basically a constant of integration, and this is we have calculated at t equal to 0. Correct? Fine. And now you see from equation number 3, this equation number 3 which we have, because you see we have equation number 3, equation number 4, equation number 5. We have first considered the equation number 5 because we have to study what is the equation of motion because of the application of electric field, and we want to see the action of electric field. And you see, because of the action of electric field, your particle is accelerated along z directions, right? In the previous case, you see then there was no electric field, was the particle was moving with a constant velocity. There was no acceleration. Particle was moving with a constant velocity along z direction, and because of that you were having the helical path. But here you have a helical path, the particle is accelerated, and because of this acceleration we will have a very important effect which we would like to study, that is known as the electric drift, which I will discuss. But here you see this equation, I take this equation number 3. So this is the equation number 3 which I obtained from equation of motion, right? And this equation of 3 I'm writing here. Look at this equation number 3. Mvx dot equal to qex plus qbvy, the same equation which I wrote here. You can see mvx dot equal to qex plus qby. So the same equation I am writing here for your reference. And now I'm taking, I divide by m both the side by mass of the particle. So we get vx dot, and I'm again differentiating this equation with respect to t. So you see, I'm differentiating this equation. So this is that second order, the time derivative of Vx dot. So this is basically d by dt of Vx dot. So once again, it will be a second order differentiation. So it is Vx double dot, which you know. And this is basically, you see here, I write down this term. This term I'm writing first. QB over M is constant, and differentiation of Vy with respect to T is Vy dot, right? And you see, this is a constant term, so the differentiation of this constant term is zero, because charge carried by the particle is constant, your Ex is constant because electric field is constant, and mass of the particle is constant because it is not moving with a relativistic speed. You see, your particle is not moving with a relativistic speed, so your mass of the particle is also constant. So there the time derivative of this constant term is zero. So I have a Vx double dot is equal to, you can see, a QB over M into Vy. Okay, and you see this Vy dot, of course it is Vy dot, and you know this Vy dot, we can write down this equation. So you see this expression which I obtain here. Look at this equation, and Vy dot I calculated from the equation number 4. What is Vy dot? Vy dot is minus QB over M into Vx. This you can calculate from equation number 4. Vy dot is equal to minus QB over M into Vx. So this expression which I wrote here, you can see. So I write down this Vy dot, which I use this expression. So I use this Vy dot. Once again, you please look at this. I calculated Vy dot from here. So V by using equation number 4, Vy dot is minus QB over M into Vx. So that expression I am keeping here, and you can see that there is a minus sign, so I'm keeping here minus, and QB over M into QB over M, both the times they are multiplying, so it becomes a square. So QB upon M square into Vx. So this is the term which we know. This is QB over M is basically, you know, this is a cyclotron frequency which we have already defined, because you know that electrons and ions are gyrating along the field lines. And the frequency of gyration is known as the Larmor frequency, and we have defined the Larmor frequency equal to QB over M. This you people know. So I can write this equation number 6 in terms of Larmor frequency. So look at this actually here. You see, I wrote this equation once again here. So Vx double dot is minus QB over Vx, and we will define here this term. But before we define this term, let me calculate Vy dot, right? You see, so Vy dot. See, I have already defined the Larmor frequency here. So that is, I'm defining here. But before we define the Larmor frequency here, once again, your equation number 4, I write this equation number 4. You see, Mvy dot equal to minus Qb over Vx. Because I have already calculated Vx double dot. Now I want to calculate Vy double dot. You see, right? To calculate Vy double dot, you see this equation number 4, Mvy dot equal to minus QB Vx. You look at this expression here, this expression number 4, which I wrote here, the same equation I'm writing, I'm using the same equation. So I'm writing this equation for your reference, this equation number 4. I'm rewriting and I'm defining Vy dot, because I divide M by mass of the electron both the sides, or mass of the particle, I would say. So Vy dot is minus QB over M into Vx. Again, you differentiate with respect to T, both the sides. So you see this Vy double dot, and this is a constant factor. So I'm writing the constant factor, and time derivative of x component of the velocity is Vx dot. And you see, I have equation number 3, which is I'm writing for your reference. Mvx dot equal to Qex plus Qvvy. So this is the expression number 3, which is already derived here. So once again, I'm using this equation number 3 to find out the value of time derivative of x component of the particle velocity. So here I'm writing Vx dot, and this Vx dot I substitute here. This is Vx dot, and this Vx dot is I'm keeping the value of Vx here. And now you see, so I have calculated Vx double dot, right? And I have calculated Vy double dot. second order derivative of the x component of the particle velocity with respect to t, and second order derivative of y component of velocity with respect to t, that is the time derivative, second order time derivative, I would say. Now you see I'm defining the cyclotron frequency. So when you define the cyclotron frequency, we have because cyclotron frequency is always positive. So we have to write down the magnitude of Q, because we cannot write minus sign, because if you have electrons, people write minus EB over M. So in order to avoid this difficulty, we write magnitude of Q B over M. So you can see your equation number 6 is, this is the equation number 6, which we have already derived, you can see, and this is nothing but your cyclotron frequency. So I define equation number 6 in terms of cyclotron frequency. This is Vx double dot equal to minus omega c square Vx. And this is a very famous differential equation. This is a second order differential equation with a constant coefficient, you see, which you are familiar, and its solution is of this type. This second order differential equation also we have used when you consider uniform magnetic field, and we have derived this expression, the same expression we are also obtaining in this condition. But you see that this is a second order differential equation with a constant coefficient. This is Vx0, and its solution is given by Vx is equal to Vx0 cosine of omega ct plus phi. Phi is a phase angle, and this is omega c is basically a cyclotron frequency, right? And here Vx0 is a constant. Now using equation 3, the same equation you see, because I calculated Vx, right? So now I should calculate Vy. I calculated Vx double dot, I calculated Vy double dot, now I calculated Vx, that is the x component of the particle velocity, right? And now I want to find out the y component of the particle velocity. To find the y component of the particle velocity, I am using equation 3. This is the equation 3 which we have used frequently for derivation. So you see this equation, mvx dot equal to qex plus qbvy. So I'm using this equation, and I will find out Vy from this equation number 3. So you can see here the same equation I'm rewriting for your reference, so you can understand here. So you see this is the same equation I'm writing here, and now I want to find Vy, right? So you see I write Vy, and I divide by QB both the sides. You see this is the equation which you can write. So you can see that Vy, so if you make this, simplify this equation, you get Vy equal to mqb Vx dot minus Ex V over V. And you can see this again, you can see that this is nothing but 1 upon 1 upon cyclotron frequency, you see, because QB over M is a cyclotron frequency. So this is M over QB, that will give you 1 upon omega C. But when you write omega C, you have to write down plus or minus sign. Here I please mention, I mentioned this sign because if you have an electron, you see, you have to write down, of course, cyclotron frequency is always positive. But when you write down the expression of Vy, you should take care about the sign here. You see here Q. If you have an ion, you have a plus Q. If you have an electron, you have a minus Q. So to take care about the sign, here I introduce a plus or minus sign, and I write down for this plasma frequency 1 upon omega C Vx dot minus Ex over V. So this is again the same equation, and as you see the same equation I am writing here. This is the equation, this is the Vy, the same equation is written here. Same equation is written here. And now we know Vx dot. We already calculated Vx dot. This is Mvx dot V. We know these equations, right? So from this equation, you can calculate Vx dot is equal to Qex divided by M plus Qb divided by M into Vy. So I am calculating, and again you see this Vx dot. There is another form of Vx dot which we have calculated. You see this Vx is equal to Vx0 cosine of, this is the term, this is the equation. You see Vx is equal to Vx0 cosine of omega ct plus phi. You take the time derivative, that is d by dt of Vx, that is Vx dot. So time that this is Vx0 is constant. So differentiation, so Vx0 and differentiation of cosine term is a sine term. You will have a minus sine term, right? Because if your differentiation of cosine function, that will give minus sign. So you see here, I differentiate this term here, Vx dot. This is Vx dot. So Vx is this. So this is Vx0 with a minus sign because differentiation of cosine is minus, and you have omega c a multiplier and sine of omega ct plus 5, and you have a minus ex over b. You see this minus ex over ex is x component of the electric field. Please remember, it is x component of the electric field, which is constant. It does not change with respect to time t here. It is a constant. So here you have this Vy component, and you see this is the minus sign. And here the outside we have a plus or minus sign. So you can write this Vy is minus or plus. Vx0, this omega c cancel, so it is sine omega ct plus 5 minus ex over b. Here plus or minus sign represent this. So you see this is your Vy, and you have your Vx component. So this is basically writing this Vx, this is Vx. You see this is your Vx. Vx is Vx0 cosine of omega ct plus 5, and Vy is this. Vy uh, is equal to minus or plus Vx0 sine omega ct plus 5 minus Ex over B. So this equation, you see equation 9 and equation 10, you can write down the take the square of this. So if you take a Vx square, you see this Vx which you already calculated. So take this. So it is Vx0 cos square of omega ct plus 5, which I can write down here, Vx square plus Vy square. This is Vy plus this is minus Cx by B. So I'm taking this, I can rewrite this equation. So Vy plus Ex over B will be equal to what? Vy plus Ex over B is equal to minus or plus Vx0 sine omega ct plus 5. So if you take a square, if you take the summation of Vx square plus Vy plus Exb whole square, and this is basically, this is a cos square plus sine square. Cos square theta plus sine square theta is always 1. So you will have got a Vx0 square. So we can say that Vx square plus Vy plus Ex over B whole square is equal to Vx0 square, and Vx0 square we consider as V perpendicular. Vx0, and that is equal to V perpendicular square. So V perpendicular is simply a square root of Vx square plus Vy plus Ex over B whole square. You see, when you consider the only magnetic field, that there is no electric field. In the previous case, when there was a motion of a charged particle in a uniform magnetic field, Ex was 0. So you can calculate V perpendicular square equal to Vx square plus Vy square, and that is equal to Vx0 square, which we have already developed in the previous classes also. And we have defined that V perpendicular is the velocity of the particle projected in xy plane. So please remember, this V perpendicular square is simply Vx. So V perpendicular is Vx0, and V perpendicular is basically a velocity of the particle projected in xy plane, right? And you see this xy plane, please remember, and you have your magnetic field is applied along z direction. So now you can see the equation which we have calculated, the equation number 9. Equation number 9 is basically giving you the x component of the particle velocity. So, and which is a function of t, which you can see. So x component of the particle velocity, you can see this is the This is the x component. Vx equal to Vx0 cosine of omega ct plus phi. So this is your x component to particle velocity, right, in presence of combined field, which I write here. And now I integrate this equation with respect to t both the sides. So I will get the position coordinate x of the particle. You see, this is Vx is simply dx by dt, and you integrate with respect to t, and you see this integration of Vx0 cosine of omega ct plus phi with respect to t, and I am writing the x0 is basically a constant of integration which represent the x coordinate of the particle of plasma at t equal to 0 second. Right, z0 is basically a z coordinate of the particle, which we are considering at t equal to 0. Similarly, y0 is the y component of the particle of plasma at t equal to 0, right? So I can simply write down this integration is x. This is the integration of cosine of omega ct plus phi, which you remember that integration of cosine, and you have a 1 upon omega c term. So it is Vx0 upon omega c sine omega ct plus phi, which is known to you, and you have x0, correct? And similarly, you have your equation for y component, which you written here, this equation, right? You have Vy, that is nothing but dy by dt. Dx is dx by dt. So d by dt of Vy, and if you integrate with respect to t, you will get the y component of the particle at time t. So you can see here, I integrate, this is the equation. You see there is a minus plus sign because of, you see we have considered here, see there is a minus or plus sign here, and now you integrate with respect to t. So you see that Vy is dy by dt, and you integrate with it, there is a minus or plus sign, so I'm writing minus or plus sign. Vx0 is constant, so I write Vx0 is constant, and you have to integrate sine term with an argument omega ct plus phi with respect to t, and you have your the term minus ex over b. You have to integrate with respect to t, plus constant of integration is y0, which is giving you the y component of the position of the particle at t equal to 0, where particle is projected, right? So this is giving you y, because it is basically integration. So with respect to, so this is y, and so this is giving you y, and you see integration of sign is minus cos. So if you get a minus sign, so there is a minus sign, so it becomes plus. If it is a plus sign, it becomes a minus. If you take a minus sign and there is a minus of sign because of the integration term, so there comes a plus. If you take a plus sign here and because of the integration there is a minus, and so the sign is inverted and you see it's plus or minus. Vx0 1 upon omega c will appear because of this integration term, cosine of omega ct plus 5. This is the integration with respect to t, so it is ext over b plus y0. So I can rewrite this expression here. So this is nothing but x minus x0. So you can see this x minus x0 equation I can write down here, and you see this is you see this is very important. You see this, I introduce the term Larmor radius, because you see this term Vx0 over omega c. Vx0 is nothing but v perpendicular component, that is the particle velocity projected in xy plane. So Vx0 is V perpendicular. So it is V perpendicular upon omega c. V perpendicular omega c is basically Larmor radius. You see particle is gyrating along the field line with a Larmor radius, which we have defined in the previous lecture. And we know it is Vx0 upon omega c. So you see the Vx0 is V perpendicular. V perpendicular divided by omega is a Larmor radius, which I wrote here. So x minus x0 is RL sine omega ct plus 5. This equation is well known, it is familiar to you. We have also obtained the same equation in a previous classes where there was no uniform electric field, but now we have applied the electric field. You see your y component, basically your y component, you see is consisting this term. You see, this is very important. Your x component is appearing here and is a function, it is associated with the time t. So you see it is y minus y0. You have the plus or minus sign, RL cos omega ct plus 5, and this is the term ex over b into t. So I can write down this expression in this form. And now you see this equation, this equation 11 and equation 12 are representing the basically equation of circle. So I may write down x minus x0 minus y0, and I rearrange this term y minus y0, and because of this minus sign, ex t over p square is equal to rl square. This you can verify because sine square theta plus cos square theta is equal to 1, so it will give you rl square. So again, I take the minus sign common here. You see, and this is basically you get x minus x0 square plus y minus y0 ext over b whole square. This is the equation. You see, in the previous case where there was no electric field, we were getting the equation x minus x0 square plus y minus y0 whole square is equal to rl square, which describe the equation of circle whose center is x0 and y0, which is known as the guiding center. And we found that the guiding center was moving with a constant velocity. Here x0 and y0 does not depends upon time t, because there is no electric field and particle was not at all accelerated. So particle was moving with a constant velocity. So in addition to the circular motion, there was a linear motion, but the motion was constant. You have a constant motion along z direction, and your guiding center x0 and y0 were time independent. But here you see here, when you applied the electric field, what you observe, your x0 is not affected by the time, but you see your y coordinate of the center is changing with time in a negative y direction. Why? Because y minus y, you see there is a minus sign. So please remember that your y coordinate of the center, y coordinate of the guiding center, the center of the circle is one of the guiding center. This center, you see, has a coordinate. When there is no electric field, the coordinate is x0 and y0. But moment you apply the electric field, the coordinate of x coordinate is x0, but y coordinate is y0 minus ex over t. So you see your y coordinate is basically, you see it is changing with respect to t. So your y coordinate is changing with time t in a negative y direction, because it is y minus y0, and you see y0 minus ext over b. So it is changing in the negative y direction, and this indicates that the guiding center is drifting with a velocity. Which velocity? Ex by b. You see, this ex over b is basically is not the velocity. If you will see, we'll see that the dimension of ex over b also. So I would say that since your y component or y coordinate of the guiding center is changing with time, if there is an electric field, then the y component of the guiding center is changing with time, and it is changing in negative y direction. This indicates that guiding center is drifting with a velocity in with velocity, that is the guiding center velocity, that is ex over b in a negative y direction. So your particle is drifting in a negative y direction, I would say. So here you let us verify with a vectorial representation. So if you can see that this ex over b is simply nothing but it is a product of e cross b over b square. Let's see, this is ex over b. This ex over b is known as the drift velocity of the guiding center. So guiding center is drifting with some velocity. So the velocity with which the guiding center is drifting in a negative y direction is given by a ratio of ex over b. So your x component of the particle velocity so not particle velocity, or x component of the electric field, which is uniform when x component is constant. So ex over b is a constant term, b, because b is constant, ex is constant. But because you see it is associated with a factor time t, you see that's why your y coordinate is changing with respect to t, and it is drifting in a negative y direction. And you see I can define your the drift velocity of the guiding center. The guiding center is drifting in a negative y direction, is given by a vector product of E cross B over B square. You see I write your vector E, because it is given in xz plane, so I write EXI plus EZK. And your vector B, that is your magnetic field, is applied along z direction, so I write down in the only z direction. So if you take the vector product of E cross B, so I can see EXI plus EZK cross BK. And now you see if you take the product of this, that is EXB, and it is I cross K, and I cross K is always minus J. So the first term will give you EXB in a minus J direction. And you see EZ cross B and EZB, K cross K, K cross K is 0, right? Because theta is 0. So here K cross K is 0. So this factor disappear, it will vanish. So the only the one term which is giving you the contribution of I cross K is minus J. So your E cross B is what? E cross B is EXB over minus J. So it is EXB with a minus J and over B square. So this B over B square cancels and gives you EX over B with a minus vector J, right? So if you interpret this equation, the guiding center, the drift velocity of the guiding center is given by, you see Ex over B in the direction of vector minus J. So my minus J is basically a negative y direction. So here the particle is drifting in a downward direction. And please remember the drift velocity of the particle, I say particle, you see the charge particle is drifting in the downward direction. And you see that the drift velocity is independent of the charge carried by the particle, it is independent of the mass of the particle, it is independent of the velocity of the particle. It is simply depends upon the strength of the electric field, the strength of the magnetic field. And this we want to understand the physical interpretation of the electric drift is playing very important part to understand motion of charged particle in a uniform electric and magnetic field. So in my next lecture, I will give you the physical interpretation of electric drift. What is the electric drift? On which factor electric field depends, which because I said that either the particle is a heavy or a particle is slow, or I'm sorry, so it's not slow, particle is light. If a particle is a heavy or a particle is a light particle, or a particle is moving with a higher velocity or a particle is going with a lower velocity, irrespective of their charge, irrespective of their mass, irrespective of their velocity, the drift velocity is constant. And we will see that particle, the guiding center is drifting in a negative y direction. You see in the previous case when we discussed the problem where there was only uniform magnetic field, the particle was simply moving with a constant velocity and the guiding center was not at all drifting. But here, because of the application of electric field, your guiding center is drifting in a negative y direction with the velocity. I would say the magnitude of velocity is by Ex over B. And this we want to understand. We want to understand the physical interpretation of the electric drift. So in the next lecture, I will give you the physical interpretation of the electric drift. I will stop here and thank you very much for listening me. Thank you.